There is a number NASA has never said out loud in a press conference, and it is not the size of an asteroid. It is a percentage. It is the fraction of city-destroying space rocks we have actually found out of all the ones already out there, silently crossing our orbit, unlit, untracked, unnamed. That number is small, smaller than most people would accept if they understood what it meant. And in February of this year, the woman whose literal job title is planetary defense stood in front of the world's largest scientific body and said, on the record, what she loses sleep over, it was not the asteroids we're watching, it was the ones we're not. Her name is Dr. Kelly Fast, and at the time she was NASA's acting planetary defense officer, which sounds like a fictional title from a disaster film, but is, in fact, an actual government position, occupied by an actual scientist, whose actual job is to look into the dark and tell the rest of us what she sees. Speaking to the American Association for the Advancement of Science in Phoenix, she said something that should have been the headline of the year, and instead barely made it past a handful of outlets. What keeps me up at night is the asteroids we don't know about. Read that again. Not the ones on the watch list, not the ones with cute designations and orbital tracking pages, the ones that don't have names yet, because nobody has seen them. And here is where the story stops being comfortable, because most people assume that if something large enough to level a city were heading toward Earth, someone, somewhere, would already know. That assumption is wrong. It has always been wrong. And this year, that wrongness came uncomfortably close to becoming a headline that would have redefined the decade. To understand why Dr. Fast's warning matters, you have to go back 4 years, to a night in September of 2022, when NASA did something no civilization in human history had ever attempted. It sent a spacecraft, roughly the size of a vending machine, on a collision course with an asteroid on purpose. Not to study it, not to photograph it, to hit it, hard, at around 14,000 miles an hour. The spacecraft was called DART, the Double Asteroid Redirection Test, and its target was a small moonlet named Dimorphos, orbiting a larger asteroid called Dimorphos, roughly 7 million miles from Earth. Neither asteroid posed any threat to us. That was the point. This was a test, run on a target that couldn't hurt anyone, to answer a question that could one day save everyone. The question was simple to ask and terrifying to leave unanswered. If we ever found an asteroid on a real collision course with Earth, could we actually do anything about it? Could humanity, with all its rockets and telescopes and calculations, reach out across millions of miles of empty space and physically change the path of a solid rock moving fast enough to end a civilization? Before that night in 2022, the honest answer was, we think so, theoretically, probably. After that night, the answer changed, and it changed by more than anyone expected. NASA's own mission planners had modeled a range of outcomes before impact. A modest success would have shifted Dimorphos' 11-hour, 55-minute orbit around Didymos by a handful of minutes. Anything above 10 minutes would have been considered a strong result. What actually happened was not a modest success. The impact shortened Dimorphos' orbital period by approximately 32 minutes. Sit with that number for a second. Not 10, not 15, 32. A single vending machine-sized spacecraft crashing into a 500-foot rock at hypersonic speed altered its orbit by more than 3 times the threshold NASA itself considered a win. This is not chaos. This is proof. Humanity had just demonstrated for the first time ever that we are not helpless in front of the sky. But here is where it gets more complicated. And this is the part almost nobody outside the planetary defense community actually understands. The reason Dimorphos moved so much farther than predicted wasn't purely the force of the impact itself. It was something else, something that happened in the milliseconds after collision, something scientists call the momentum enhancement factor, or beta. When DART slammed into Dimorphos, it didn't just push the rock. It blasted a massive plume of debris, rock, and dust off the asteroid's surface, and that ejecta, flying off at high speed in the opposite direction, acted like a second engine, adding extra thrust to the deflection, on top of the original impact. In simple terms, the asteroid helped push itself out of the way. That is either the best news planetary defense has ever received, or the most dangerous assumption humanity has ever made, and right now, we genuinely do not know which one it is. Because here's the problem nobody wants to say plainly. To calculate beta with real confidence, scientists need to know the exact mass of Dimorphos, and DART never measured that. It couldn't. It was a one-way mission. The spacecraft was destroyed on impact by design, and everything we know about the aftermath has come from millions of miles away, through ground-based telescopes squinting at a distant point of light. We know the orbit changed. We don't fully know why it changed exactly as much as it did, and that means we don't fully know whether the same strategy would work the same way on a different asteroid, made of different material, with a different internal structure, at a different size. Think about what that means. Humanity's entire proof of concept for saving itself from an asteroid impact is currently sitting on an assumption we have not yet been able to confirm. That confirmation is coming. It's coming faster than most people realize, and it's coming right now while you're watching this. The European Space Agency's follow-up mission, Hera, Launched from Cape Canaveral in October of 2024, and after a gravity assist flyby of Mars in March of last year, it has spent this year completing the deep space maneuvers required to physically rendezvous with the Didymos system. As of this year, Hera is not months away. It is not years away. Its arrival at Didymos has been moved up ahead of schedule to November of this year. In a matter of months, a spacecraft is going to arrive at the scene of humanity's first planetary defense experiment and finally measure the crater, the mass, the internal structure of Dimorphos, and give us the real number behind Beta. When that number comes back, we will know for the first time in human history whether our one successful planetary defense test was a repeatable strategy or a lucky roll of the dice. Everything currently being planned for the future of asteroid deflection is waiting on that answer. And this is where the story stops being about one asteroid and starts being about all of them. Because while Hera has been quietly crossing the solar system to check humanity's homework, something else happened. Something that turned an obscure planetary defense exercise into a live, real-time test of the entire warning system. And most people watching the news at the time had no real understanding of how close it actually came to being serious. On December 27th, 2024, an automated telescope system in Chile, part of a network called Atlas, designed specifically to catch objects other surveys miss, picked up a faint moving point of light. It was cataloged with a forgettable name, 2024 YR4, and for a few weeks, it sat quietly in a database, one more entry among thousands. Then the orbital calculations came back, and it stopped being quiet. By February of last year, as more observations refined its trajectory, the impact probability for 2024 YR4 striking Earth on December 22nd, 2032 climbed. Not slightly. It climbed to 1%. Read that number again, because context matters here. That was the highest impact probability ever recorded by NASA's own tracking systems for an asteroid of its size. Every previous object that had ever triggered public concern had eventually been ruled out within days or hours of extra data. This one didn't behave that way. It kept climbing. For a brief tense window, planetary defense scientists around the world were doing something they almost never have to do, taking a specific date, 8 years in the future, seriously. The asteroid itself was estimated at somewhere between 130 and 300 feet across, later refined using infrared data from the James Webb Space Telescope to a tighter range of roughly 174 to 220 feet, about the size of a 10-story building. That is not an extinction-level object. It would not end civilization. But an object that size, moving at tens of thousands of miles an hour, striking a populated area, would flatten a city, not damage it, flatten it. This was, in the truest sense of the words, NASA itself sometimes uses, a city killer. But here's where it gets worse, and this is the part that should genuinely unsettle you. As additional observations came in through the following weeks, the Earth impact risk was walked back, and by late February of last year, it had dropped dramatically, eventually falling to a statistically negligible 0.04%. Earth, for this particular rock, on this particular date, was safe. The public exhaled. Most news coverage moved on. And that is exactly the moment when the real story quietly kept unfolding, almost entirely out of view. Because as the Earth impact numbers fell, a different number rose, the Moon. Refined trajectory calculations showed that while 2024 YR4 would miss Earth, it had a real, non-trivial chance of striking the Moon instead, on that same date in December 2032. By April of last year, that lunar impact probability sat at 8%. By June, new Webb Space Telescope observations pushed it to 3%. Think about what a 4% chance of impact means when you're talking about a solid object roughly the size of a 10-story building, on a known, tracked, calculated collision course with a body 240,000 miles away. Scientists began quietly discussing what a lunar impact of this scale would actually look like from Earth, and the numbers were almost cinematic in themselves. An impact carrying the destructive equivalent of a mid-sized thermonuclear detonation, releasing energy roughly 1 million times greater than the last significant lunar impact humanity observed back in 2013. If it hit, it would not be a scientific curiosity buried in a research paper. It would be visible from your backyard, with the naked eye. A flash on the face of the Moon, caused by a rock we found less than 8 years earlier, tracked the entire way. And then, this year, something happened that almost nobody outside the planetary defense community fully absorbed. Between February and March of this year, using the James Webb Space Telescope to capture some of the faintest asteroid observations ever recorded, before 2024 YR4 slipped out of view entirely for years, scientists refined its orbit one final time. The new data ruled out the lunar impact as well. The asteroid is now projected to pass the Moon at a distance of roughly 13,200 miles, a clean miss. Earth is safe. The Moon is safe. The story, on paper, has a happy ending. But here's the part that should actually keep you up at night, more than any single asteroid ever could. This entire sequence, discovery, panic, near-miss headline, quiet resolution, took 13 months from first detection to final clearance. And for a solid stretch in the middle of it, the world's leading experts were seriously modeling a scenario where a building-sized object struck either our planet or our closest celestial neighbor on a specific calculated date, less than a decade away. And this object was found by a purpose-built early warning telescope network doing exactly what it was designed to do. This was the system working. This was the best-case version of detection. And it still took over a year of uncertainty, shifting probabilities, and international scientific tension to fully rule out. Now ask yourself the question Dr. Kelly Fast is already asking, what about the ones that aren't found by a purpose-built network? What about the ones too dark, too small, too slow-moving against the star field, or approaching from the glare of the sun, where ground-based telescopes are functionally blind? According to current estimates from NASA's own planetary defense program, only a fraction of the estimated population of near-Earth objects in the size range capable of a city-level destruction have actually been cataloged. The rest are out there, untracked, unnamed, following orbits nobody has calculated because nobody has seen them yet. This is not a hypothetical fear invented for dramatic effect. It has already happened in living memory twice. In 1908, an object believed to be somewhere between 200 and 400 feet across exploded in the atmosphere above the Tunguska River in Siberia, flattening roughly 800 square miles of forest, an area larger than many major cities, with a force estimated at over 1,000 times that of the atomic bomb dropped on Hiroshima. There was no warning. There was no telescope watching. It simply arrived. And in February of 2013, a much smaller object, roughly 60 feet across, entered the atmosphere over Chelyabinsk, Russia, undetected until the moment it exploded, injuring over 1,500 people, mostly from flying glass shattered by the shockwave, in a city nobody had evacuated because nobody knew to. That object was small enough and approached from an angle close enough to the sun's glare that every ground-based detection system on Earth missed it completely. It was found only after it had already arrived. This is the blind spot Dr. Fast was describing in Phoenix, not a theoretical gap in the data. A demonstrated, historically proven gap, one that has already produced 2 real impact events within the last 120 years, and one that current infrastructure still cannot fully close. Her stated mission, in her own words, is to find asteroids before they find us. But the tools to do that at scale, the tools capable of actually closing the gap that let Tunguska and Chelyabinsk through, are not fully operational yet. They are still being built. The centerpiece of that effort is a spacecraft called the NEO Surveyor, and its story is its own quiet drama. It is NASA's first space telescope purpose-built, from the ground up, for exactly one job, finding hazardous asteroids and comets before anything else does. Unlike traditional telescopes, which detect asteroids by the sunlight reflecting off their surface, NEO Surveyor will hunt in infrared, detecting the heat these objects radiate, which means it can find dark asteroids, the ones that reflect almost no visible light and are functionally invisible to most existing search systems. It is designed to be positioned nearly 1 million miles from Earth, at a gravitationally stable point between our planet and the sun, giving it a vantage point free from the glare that let Chelyabinsk through undetected. Its stated goal, mandated by Congress, is to catalog at least 2/3 of all potentially hazardous near-Earth objects larger than 460 feet across within its first 5 years of operation. And here is the escalation nobody in the press seems to want to say plainly: that telescope does not exist yet. It is not in orbit. It is not scanning the sky. As of this year, it is still under construction at the Jet Propulsion Laboratory in California, targeting a launch no earlier than September of 2027, more than a year from now, which means that for the entirety of this year, and likely well into next, the exact blind spot Dr. Fast described in Phoenix remains exactly that: a blind spot, unclosed, unmonitored, waiting. This is where the story stops being about telescopes and starts being about politics. And this is the part almost nobody connects to the headlines about asteroids, because on the surface, they look like 2 completely unrelated stories. But they are not. For more than a year, NASA operated without a permanent Senate-confirmed leader, cycling through acting administrators while its budget became a political battlefield. The proposed federal budget for this fiscal year sought to cut NASA's overall funding by close to a quarter and slash its science budget by nearly half, threatening to end dozens of active research and monitoring programs in the process. The Jet Propulsion Laboratory, the very facility building NEO Surveyor, the facility responsible for tracking 2024 YR4 through its entire 13-month drama, laid off hundreds of staff, roughly 1/10 of its workforce, following similar cuts the year before. Read that again. The lab responsible for finding the next Tunguska before it happens, was shrinking its own workforce, while the world's most alarming asteroid in over a decade was actively being tracked through its facilities. It was only in December of last year that the U.S. Senate finally confirmed a permanent NASA administrator, Jared Isaacman, a private astronaut and entrepreneur with no prior government experience, arriving to lead an agency that had just endured a year of budget uncertainty, workforce reduction, and organizational disruption. He inherited an agency at a crossroads, one still trying to stabilize its workforce and its science programs at the exact moment its most quietly important early warning telescope was racing toward a 2027 launch window it could not afford to slip. Whether that stabilization holds, whether NEO Surveyor launches on schedule, whether planetary defense funding survives the next budget cycle intact, remains, as of this year, genuinely unresolved. And underneath all of this sits a question that almost no government official likes to answer directly, on camera, without qualifiers. If NEO Surveyor had already been operational in 2013, would Chelyabinsk still have happened without warning? If it had existed in 1908, would Tunguska have arrived as a surprise, or as a headline the world saw coming for months? Nobody can answer that with certainty. But every year the telescope's launch slips, every year budget cuts threaten the labs responsible for tracking what's already been found. Is another year, the blind spot Dr. Fast described stays open just a little longer. Now, bring this back to Hera, quietly closing in on Didymos as you watch this, because this is where the entire narrative folds back on itself. Even if NEO Surveyor launches on schedule in 2027, even if it finds every dark, undetected city killer currently hiding in our blind spot, that only solves half the problem. Finding a threatening asteroid means nothing if we cannot reliably move it. And right now, the entire foundation of our ability to move one rests on a single data point, DART's 32-minute orbital shift on Dimorphos, and an assumption about ejectophysics that has never been independently confirmed. This is not a comfortable place for a civilization to be standing. We have one successful test, we have one unconfirmed multiplier, and we have a follow-up mission arriving in a matter of months to tell us whether the multiplier was real science or an extraordinary coincidence. Because if Hera arrives at Didymos this November and finds that Dimorphos' mass was far higher than assumed, that beta was smaller than calculated, that the ejectoplume contributed less momentum than credited, then the entire deflection playbook currently sitting in NASA's planning documents needs to be rewritten for every future asteroid, on every future mission, under whatever time pressure that future threat allows us. And if a real threat is discovered before that rewrite happens, humanity may be forced to attempt a deflection mission using a strategy we only think we understand. This is not a distant, abstract concern reserved for scientists in conference rooms. It sits directly beside a genuinely uncomfortable calendar fact. In April of 2029, an asteroid named Apophis, roughly 1,900 feet across, more than large enough to cause continental-scale devastation, will pass Earth at a distance of only about 20,000 miles, closer than many communication satellites, and one of the closest approaches by an object of its size ever observed. NASA has already ruled out any impact risk from Apophis for at least the next century, following refined radar observations. It will not hit us, but its close pass will serve as an unplanned, real-world stress test of humanity's tracking and observation capability on an object large enough that a miscalculation would matter. At a moment when the deflection technology meant to respond to exactly this kind of threat may still be running on unconfirmed physics. Step back and look at the full shape of what is actually happening, because no single headline captures it. In 2022, we proved we could hit an asteroid. In 2024, an automated telescope caught a genuine, if ultimately non-threatening, city killer candidate and walked the world through a rare, real-time 13-month planetary defense drama, culminating only this year in its final, quiet resolution. In 2026, NASA's own planetary defense chief stood in front of the scientific community and said, plainly, that the real danger is what remains unseen. The telescope built to close that gap will not fly until 2027 at the earliest, inside an agency that spent over a year without permanent leadership and is still absorbing historic budget cuts. And the spacecraft capable of finally confirming whether our one successful deflection test can actually be trusted is, right now this month, closing the final distance to the asteroid we hit 4 years ago, arriving in November to deliver an answer we have been waiting on since the moment of impact. None of these threads are separate stories. They are one story, unfolding in real time, across multiple space agencies, multiple governments, and multiple years, and it has been sitting mostly in the background of public attention, buried under headlines about rocket launches and Mars timelines, while the actual defining question of this era in space policy remains completely open. Not whether an asteroid is coming. Nobody credible is claiming that. The question is whether when one eventually is found, whether that's next year or in 50 years, humanity will have finished building the eyes to see it in time and finished proving the hand capable of moving it once we do. Dr. Kelly Fast said, "What keeps her up at night is the asteroids we don't know about." What she didn't say, because she didn't need to, is that the tools built to end that particular kind of sleeplessness are still under construction, still waiting on budget approval, still months or years from being fully operational, while the clock behind them keeps running regardless of funding cycles, political transitions, or how quickly any of us are paying attention. Hera will reach Didymos this November. NEO Surveyor is scheduled for no earlier than September 2027. Apophis makes its close pass in April 2029. Each of those dates is fixed. Nature does not negotiate deadlines with congressional budget committees. So the real question isn't whether the sky is dangerous. It always has been. The real question is simpler and far less comfortable. When the next 2024 YR4 shows up, not as a near miss with a happy ending, but as something real, will we see it early enough to matter? And will we actually know for certain whether we can move it out of the way? Right now, nobody, not NASA, not ESA, not any government on Earth, can answer that question with full confidence. And until Hera's data comes back, until NEO Surveyor reaches orbit, until the next close call tests the system for real, that uncertainty isn't going away. It's simply waiting, the same way everything else out there in the dark is waiting for us to finally look.